Continuing with our 3.2 notes, these data were collected in the city of Metropolis from 1995 to 2015. Notice the little asterisk which says fictitious city. So some reasonable data, but not really true. The explanatory variable is the average unemployment rate for the year, and the response variable is the number of murders per year per 1 million people. So each data point would represent the percent of unemployment for that year matched up with the murder rate. Now I want you to notice here we have a scatter plot. Just as a reminder, we could describe the scatter plot as a moderately strong linear relationship between percent unemployed and murder rate per 1 million people per year. No real extreme outliers, perhaps that one, but probably not really any outliers. So pretty good linear model here. In the second graph we have a residual plot. Now I want you to notice in the residual plot here that we have 0 here. So the 0 here represents 0 residual, or 0 amount of difference between the actual and predicted value based on this linear regression. So for example, this point right here shows up right here on the residual plot. There is very little difference between the actual and predicted values because that point is almost on the line, so it has almost a 0 residual. This point right here has a fairly large residual. Okay, so we see this value right here, this point. We can see that there is a residual of almost 10, maybe about 11. So we can see that the predicted murder rate is about 10 or 11 less than the actual murder rate in murders per million people. Okay, so notice all the points below the least squares regression line end up in the negative residual part here, and then all the points above the least squared regression line are in the positive residual part here. So what's important about a residual plot? We would want a residual plot to show no particular pattern, to look very randomly scattered. If the residual plot looked randomly scattered, then that is a sign that the linear model was an appropriate model for these data. So let's look at this first question. First of all, I wanted to point out that I do have listed on the notes here the objectives that you are supposed to be able to do in this section. So because there were a lot of really specific objectives, I have listed them all in the notes for you. So you are to be able to construct and interpret residual plots to assess if a linear model is appropriate. And we'll get to the construct part in just a minute. So is the linear model appropriate for these data? In other words, is it okay to make a linear model? Now, this is a question we've asked before when we were talking about normal models. So let's just recall, with a normal model, we can't use a normal model for just any set of data. So let me kind of write that again. To use a normal model, we have to notice something about the distribution of data. We needed to see that the distribution of data was approximately unimodal and symmetric, kind of fairly mound-shaped. If it was fairly mound-shaped, then I could say, hey, a normal model makes sense. So I've got to do the same thing when I'm dealing with a scatter plot. When I'm dealing with a scatter plot, I need to look at a couple things. Number one, is the scatter plot of data reasonably linear? Now, it's never going to be perfectly linear, but if I see a clear downward or upward curve, then I don't want to use a linear model for that data. But is it reasonably linear? In this case, yes. Number two, I want to know if the residual plot is randomly scattered with no apparent pattern. So if the residual plot had a distinct bend in it, and I'll show you an example of that, then we wouldn't want to use a linear model. So let's talk about constructing. Okay, I've got the data for this here. So here is percent unemployed, murder rate. I've done a linear regression. That's important. You have to do the linear regression first. So you see the regression line. And I am going to go to Menu, Analyze, and Residuals, and Show Residual Plot. So the calculator will make the residual plot right below the scatter plot. And so you can check and see that there's no particular pattern in the residual plot. Now, what would it look like if there was a pattern in the residual plot? I think I have an example here, so let me see if I can find it. Long job. I think it was in this document here. Yes. So here was a case where the relationship between month and average temperature has a very clear, actually this is a cosine function we used in pre-calculus, a very clear curved pattern. So the residual plot has that same curved pattern. Now this is one where you would obviously not use a linear graph, it would be very obvious, but it actually can happen, and I'll show an example, just kind of make a little sketch. It actually, can happen that you might have a scatter plot that looks kind of like this. So let me kind of make a little scatter plot. Okay, and it has just the slightest bit of a curve, and you maybe not notice the curve, and you kind of go, okay, that looks pretty good, all the points are close. But then when you make the residual plot, it ends up looking, residual plot has to have that 0. Okay, so you make the residual plot, and here's your 0 residual, and you end up having a residual plot that has a very clear bend in it. Because you notice there's just slightly more points below with negative residuals on the ends and slightly more with positive residuals maybe in the middle, and then you get this really distinct bend. That's when you have to be careful if your residual plot shows a distinct bend. Okay, next item. Using the computer output to write the equation. So let's say you don't have the raw data. I had the raw data in my calculator, but let's say I don't have the raw data. I'm given these graphs and I'm given this output in table form from a linear regression. So this is the way a statistics package on the computer would give you. I'm going to write down here that this is computer output rather than calculator output. Okay, so what you're going to notice here, we clearly have murder rate versus percent unemployed, and I have these graphs that show me the x-axis and the y-axis, so I know which one is which. But if I didn't, the way you can tell which one is which is look right here. It says predictor, and under the predictor we have constant and percent unemployed. So this percent unemployed is the x value because it is the predictor. We use it to predict the y value. The constant is the y-intercept. So what do we find next to the x value in the equation? We find the slope. So this is the slope. The constant is the y-intercept, so this is the y-intercept here. Y-intercept. So we have percent employed is my x value, murder rate's my y value, slope, y-intercept. So I can write the equation of the line. So it looks like this. Murder rate hat, because remember we use that to say predicted murder rate, is negative 28.527 plus 7.0796 times percent unemployed. And then that's my regression equation. Now you might wonder, what are some of these other numbers here? Well, I'm going to just circle these numbers and say, don't worry about those until second semester. Second semester you'll understand what all those numbers mean, but right now we're not using them. Also, you can ignore r squared adjusted. We will not be using that number. I've never taught it, so I have learned in the past what it means, but I don't remember. Two numbers, however, you do need to know about are r squared and s. I'll explain r squared in just a minute. S, remember, was represented standard deviation when we were talking about standard deviation of x or y. This represents the standard deviations of the residuals. Sometimes it's represented by S sub e for standard deviation of the errors, because the residual is the amount of error in the prediction. So this can be, we can go ahead and label this standard deviation of the residuals. So if you look at the residual plot, I think this little number will make sense. Actually, let's define it first, and then we'll look at the plot. So we use this number when we want to evaluate the strength of the model. So the appropriateness of the model is a straight line a reasonable estimate of the graph. That is what the appropriateness means. Can I use a straight line to represent these data? The strength is how well does the data predict? How well does X predict Y? So I'm going to write that down. How well does X predict Y? So is it okay to make a linear model is the appropriateness. The strength is how well does X predict Y. So one of the things we can look at is the size of the residuals. So S, what does S tell me? It says that when we use a linear model to predict murder rate using percent unemployment, the typical amount that the predicted murder rate, that doesn't look quite like murder. I'll try that again. The predicted murder rate varies from the actual murder rate sorry for the slowness here, but you need to get this down, is 5.09 people or murders per million people. We have to think about this. The residual is in Y values because it's the difference between the predicted and the actual Y values. So you have to look at your Y units. So if you go back up here and look at what the Y units are, this is murder rate per 1 million people per year. So I need to actually say that is 5.09 murders per 1 million people per year. Okay, so that is how we interpret S. Now, if we go back and look at the residual plot, we'll see here that in the residual plot that we have residuals as high as 10 or 11 and about -9 or 10. But the typical amount of the residuals is about 5. Okay, we see a whole lot of residuals that are kind of in the +5, -5 area, and sort of that's the typical amount of variation. So that makes very good sense. So the question is that large? Kind of hard to say. If we look at the murder rate overall, we see the murder rate varies from about 0 to about 40. So typical variation of 5 is, what portion of 40? That's not terribly large, not terribly small. It's kind of in between, scatter. So fairly decent model, not super strong, not super weak. Now the other number we're going to look at is R squared. And we have here that R squared is equal to 74.8%. I'm going to go ahead and define R squared, and then in the next video you're going to see a detailed explanation of what R squared means and why it is a percentage. So right now I'm just going to define it for you, and then watch that next video, which covers the next page of the notes, to see exactly what the meaning of that. I think that'll clear things up for as far as the meaning. Okay, so what the R squared tells us is that 74% of the variation in the murder rate can be accounted for by the linear regression of murder rate. I'm having trouble spelling that word. of murder rate based on unemployment rate. So we could say also that it can be accounted for by the linear relationship between murder rate and unemployment rate. So as unemployment rate changes, murder rate changes. So we notice an increase of, as unemployment rate increases, murder rate increases. Now it doesn't increase perfectly on a linear pattern, but it has a lot of the increase, or 74.8% of the increase in the murder rate is based on its linear relationship with unemployment rate. The other, about 25% is excess variability that it has things to do with other than unemployment rate. So the other 25% or so of the variability is found in the residuals. The other approximately 25% of the variability is in the residuals. And it's based on other variables. So there's other variables contributing to the murder rate besides unemployment rate. So that would be where you find the rest of that variability. So as I said, watch the video on R squared, the meaning of R squared, and that will help explain why it is a percentage and what it's exactly telling you.